Alrighty. Good morning, everybody. Welcome back to Math 320, Calc 3. Plan for today is we are going to pick up where we left off last time, discussing Standard 1, kind of our first learning standard. We're going to be talking about more about vectors today. How do you visualize them in 2 or 3 dimensions, and what are some of the algebraic things, the algebraic properties that we can use on looking at vectors. My next office hours, I don't have any official office hours today, but I will have office hours on Monday in the hour after class, as well as from 2 to 3. And as far as homework goes, as I mentioned in my email yesterday, if you go on Blackboard, there's a new tab for practice problems, where I've posted some problems from the first 2 sections in the book that are related to what we're going to be doing today. So just to give you a sense of where we're going, we're going to be working on Standard 1 for the rest of class today, and I'm guessing a little bit into class on Monday, with the idea then that the first quiz, the Standard 1 quiz, will be next Wednesday in class. And I'll talk a little bit more on Monday about what you can expect as far as the quiz goes. So, does anybody have any questions or comments before we get started for today? Why did the yardstick tell his parents he wanted his parents to stop supporting him financially? Because the yardstick wanted to stand on his own 3 feet. Okay, so when we left off last class, I'm going to be continuing along in this Standard 1 packet. We talked about what a vector is and some of the notation that we can use for vectors. So in particular, you may recall from last time, we said that a vector in Rn is an ordered n-tuple. A1, A2, all the way up to AN. Basically saying it's like a coordinate pair, the sort of things you've been graphing in 2 dimensions for a good chunk of your mathematical life. But in Rn, we just have n components to it. And when we say that the n-tuple is ordered, that just means the order of these n terms is going to matter. If you swap the first 2 terms and leave everything else the same, you're still going to produce a new vector in Rn. And kind of the different notation that we use to refer to these vectors is typically, we said that bold V is notation for a vector, usually when you're typing it out. V with a little arrowhead above it is going to refer to a vector when handwritten. Whereas a V with no hat and no bolding meant that we have not a vector, but just a scalar value, just something that's made up of a single number. And that's where we left things off last class. So what I thought we could talk about today to start things off is how you would visualize 2 and 3-dimensional vectors. I'm going to be starting on the second page of the packet. So, first question I want to ask is how can we visualize the vector v equals -3, 5 in R2? What do you think about this? If I told you that I wanted you to graph or to draw a picture of what -3, 5 is going to look like, what would your first thought be? If you were to ask to graph -3, 5 in, say, a high school math class, what would you probably do to start things off?
Real quick, draw a horizontal line and a vertical line, and call them the x and the y axis.
Ooh, okay. So we're going to draw an x-axis and a y-axis. I think that's a good start. That kind of gives us a place where we can start trying to draw out two-dimensional things.
And then those are both kind of number lines, and you can count 3 to the left on the x one and call that the first, represent that as the first number, and then 5 up from that point.
Yeah, I like it. So if we wanted to graph -3, 5, -3 is our x-coordinate, 5 is our y-coordinate. So starting at the origin, 0, 0, we would go 3 to the left on the x-axis to give us an x-coordinate of -3. And we would go 5 up in the positive direction on the y-axis. And then this would be the point, -3, 5. And then typically, if we want to represent that as a vector instead of as a point, what we would do is we would just draw an arrow starting at the origin and have it point to that point right there. Just an arrow that starts at the origin and ends up at the point -3, 5 in the xy plane. So typically, that's kind of our most common way to visualize a vector is by drawing an arrow that represents it in this way. An arrow that somehow is going to point 3 to the left and 3 units to the left and 5 units upwards. Draw an arrow from -3, or from, let's say, the origin to -3, 5 in the xy. And that's kind of the simplest way of how you would go about trying to visualize a vector in 3 dimensions, or not 3 yet, that's the next example, in 2 dimensions like this. Any questions or comments about that? So this is all fine and dandy. I'm guessing you've probably been asked to graph these 2-dimensional points like -3, 5, oodles and oodles of times in various math courses. So here's one you may not have done before. How would we graph a point in 3 dimensions? So next thing I want to ask is how can we visualize (3, 1, -4) in R3. This one's a bit trickier because it's relatively, I say relatively, it's a lot easier to try and draw some 2-dimensional vector or 2-dimensional point like -3, 5, just by saying, okay, left and right is one of your coordinates, up and down is a second coordinate, and call one of those x, call one of those y. Where you may recall, we said that in a vector in R3, we said the first component x is in the x coordinate, the second coordinate is the y component, and the third component is the z component. And so if you were trying to think in 3 dimensions, if one of the dimensions we can try and do is to go left and right, to look at length, so to speak, and we have another dimension that goes straight up and down, giving us height, what would be another way that we could sort of try and think of, intuitively at least, having a 3rd dimension? If you've ever seen a 3D movie, in other words, what makes, and you're wearing 3D glasses and it looks like the movie's doing something weird, what's actually going on there? What's giving us that 3rd dimension of seeing things?
It comes right out of the screen, as they say in the commercials.
Yeah, it jumps out of the
Yeah.
screen at you. It's supposed to, like Starly, make you think like someone's trying to claw their way out of the movie screen. But the idea is that a third dimension that we can try and visualize is a dimension of depth. Meaning when we try and graph in 3 dimensions, we can try and go left and right for one of our coordinates, straight up and down for our second coordinate, and our third coordinate is going to try and be depth. Meaning, I want to try and draw something that may be jumping out of the board at you, or kind of trying to recede its way back into the wall. So let's see if we can do this. This is hard to do and takes a lot of practice to get good at. You will be able to tell because I still feel I am not very good at it. So let's go ahead and we're going to make one axis that'll represent height. We'll have one axis that'll represent width. So far, same as trying to graph something in 2 dimensions. And then in our third dimension, we're going to try and somehow graph on a 2-dimensional whiteboard a dimension of depth. So you're supposed to try and think of this arrow as being one that's not really going up right to down left, but it's sort of jumping out of the board at you, so to speak. And then our vertical axis is going to represent the z-coordinate. The horizontal axis is going to represent the y-coordinate. And the axis that represents depth, that's trying to jump out of the board at you, is going to be our x-coordinate. Hello.
Hi, is there more class?
Yes, there's a class going on right now here.
Okay, I'm a lab tech, so I'm supposed to be here for like 2 hours. I don't know if you mind that.
Oh, hold on just a second. Try and grasp the third dimension. You're supposed to come right here.
I work as a lab technician.
Wait, so you're supposed to be here for the next class?
Oh, for the next 2 hours. So if you don't mind, I can like sit down. Like if you don't want that, it's okay. I can.
You can, if you don't mind sitting in the corner and working quietly, that's
Sure.
fine.
Yeah.
You're not. There's not going to be like people coming in trying to talk to you, right?
No.
Okay. Then I don't mind. Okay. Sorry about that. So now we have a point, or we have a vector, I should say. Let's give it a vectory name, like a W with a hat, that has 3 coordinates: an x-coordinate that goes out 3, a y-coordinate that goes out 1, a z-coordinate that goes down by -4. So we'll start with the z. Just like with the y-axis in R2, the z-axis here, going up means positive, down means negative. So a z-coordinate of -4 means we're going to be going down by 4. An x-coordinate of positive, that's a hard one. A y-coordinate of +1 means we go to the right on the y-axis by 1 unit. And the x-coordinate of +3 means it's coming towards you 3 units. A little bit counterintuitive, but a positive x-coordinate means it jumps out of the board this way. Whereas a negative x-coordinate would mean it was receding backwards into the board and would be represented going off in this direction graphically. So, if I were to try and graph 3, 1, -4, it would end up pointing somewhere like, it's really hard to do. So, a kind of trick that you can use if you want to try and graph these 3-dimensional vectors by hand is try and draw a little rectangle between the x and the y axes. Like so. And then you can go up or down however many units you need to by traveling in the z direction. So let's go down 4 units. And it would be about here. And then we're going to draw an arrow once again, pointing from the origin to this new point. So since we have a lot of axes, I'll try and draw the vector in red here. It'll end up looking something like this, in which we've gone out 3 units in the positive x direction, 1 unit in the y direction. So we're 3 units jumping out of the board at you, 1 unit to the right, and 4 units straight down, which gives us an arrow that somehow looks something like this. In my opinion, these are hard to draw. It's easy to sort of draw like X, Y, Z axes. No. It's relatively straightforward to draw X, Y, and Z axes like this. But let's actually see what happens if we try and use a computer to try and visualize the same vector in the end. So, wakey, eggs and bacon. Give this a second to load here. I've actually got some software up in which we can try and visualize what's going to be going on here. Why is this extending down so? Okay, there we go. So this is a program. It's just something you can pull up in your browser. I'm going to have a link to it on Blackboard later today called CalcPlot3D that I like to use to try and visualize some of the 3-dimensional things we're going to be looking at in this class. Here's a function, by the way. This is the sort of thing we'll be looking at by standard 6-ish. Don't need it for now. So instead of having your typical XY plane, you could think of trying to graph something in the XYZ 3-dimensional space like this. Let's have these go out to -5, -5, -5. So I'm going to scale this so you can sort of see up to 5 units in the positive x, positive y, positive c, negative z directions. Now let's see what happens if I try and graph a vector. Which one was it? 3, 1, -4. There's our vector right there. You can give it a different color so it really jumps out. So when graphing a vector in 3 dimensions, conceptually, it's always going to be the same as what we did in our 2-dimensional example. You just plot down a point, however far in the x, y, and z directions you want to go, and then you draw an arrow that's going to start at the origin like this, and then point to, in this case, the point at 3, 1, -4. The tricky part is if you're trying to write it down on a piece of paper or draw it out on a board, where a board and a piece of paper, they're 2-dimensional surfaces. Trying to draw a 3-dimensional thing on a 2-dimensional surface requires a good amount of artistic skill. Which is why, if I were to ask you on, like, say, a quiz or something, draw out this vector, 3-dimensional vector for me, I'm going to be very unpicky. Meaning, I'm not going to be like, oh, that actually looks like it was drawn at 3, 1, -2.9. -3.9. -5. I don't do that. Considering I have trouble graphing a lot of these 3-dimensional vectors, I expect it's not going to be particularly easy for you, especially starting out. But we still can talk about what it means to try and visualize them, because a lot of what we're going to be doing, especially once we get past our first 5 standards in the class, is going to be trying to visualize 3-dimensional things that you may have only seen 2-dimensionally or 1-dimensionally in past math classes. stop for just a second and I want to see what questions you all have. This is kind of something new that I don't expect you necessarily seen before, is how to graph three-dimensional vectors like this. Okay.
So since this is kind of a 2D projection of all of the 3D plane, that means that if you just draw the arrow without drawing your dotted line boxes, it's not unique. There would be, if you graph to another point or drew a vector to another point, it would look the same.
Yeah, so let me draw another axis. Just let's say this is our x, this is our y, this is our z axis. Oftentimes in two dimensions, it's common not to label your axes. It's just, everyone understands horizontal means x, vertical means y. In 3 dimensions, I think it's good for you to get into the habit of labeling your axes like this, just to get a good intuitive sense of which axis means which direction. X means depth, y means width, z means height. But yeah, if I were to tell you, Jared, all right, Jared, tell me, give me a numerical representation of that vector. That's going to be that, in other words, fill in the blanks. That's a much harder question to do than if I were to try and do the same thing in 2 dimensions. Because you could be saying something along the lines of, maybe it's an x coordinate of 1, a y coordinate of 3, and a z coordinate of 0. Something like that. Or, keeping the same arrow, maybe it's an x coordinate of 0, a y coordinate of 3, and maybe a z coordinate of negative, 2.5. Just drawing the arrow without labeling anything, and without having like a nice computer system like this that you can kind of rotate and see maybe a little bit more intuitively, it's not easy to tell where does that arrow actually point to. Because you kind of lose some information by trying to draw a 2-dimensional picture that represents something 3-dimensional. Without labeling or trying to draw these little, say, dotted lines like this, it's oftentimes going to be a bit unclear where exactly your arrow's pointing, unless you have something like this that you can rotate and sort of see, oh, I see, yeah, it's pointing out in the x direction, it looks like, to positive 3-ish. In the y direction, maybe it's pointing, to positive 1. In the z direction, it looks like it's pointing down to about negative 4. So if you have sort of this 3-dimensional thing that you can rotate, it becomes a lot easier to see where does your arrow actually point to. But without this 3-dimensional thing you can rotate and have fun with, just from drawing your axes and a single your vector arrow and nothing else, it can be very difficult to sort of tell where is your arrow actually going to be pointing. Any other questions or comments? Okay, so how do you think we would go about trying to graph a vector in R4 now? How do you think we would go about trying to draw a 4 or a 5 or a 6-dimensional picture on the board? There's a simple answer. We don't. It's hard. 2 dimensions isn't so bad. 3 dimensions is hard. 4 dimensions, I don't know, if you want a 3-dimensional space that has a time component to it shifting over time, maybe. But that sounds pretty fancy to me. And not something we're typically going to be doing. So visualizing vectors really only works with like 2 and 3-dimensional vectors. We could talk about having vectors in higher dimensions, like in R4 and R5, etc. But typically those are not going to be ones that we try and visualize because our mind isn't our mind isn't really equipped to try and visualize things in 4 or higher dimensions, so to speak. Figure out a little bit how to get used to working with this. So now we've talked about how to graph vectors in 2 or 3 dimensions. Let's talk about 2 different ways to try and visualize the same vector. And that typically, there's oftentimes going to be 2 types of vectors that we're going to be able to talk about. The first being the idea of something called a position vector, and the second is going to be something called a displacement vector. A position vector, we can treat a vector v equals v1, v2, up to vn in Rn as a position vector by treating it the way that we looked at in our first 2 graphs, thinking of the vector as being something that starts at the origin and then points to whatever point corresponds to these coordinates. We're going to treat it as a position vector by thinking of it, not treating again, as pointing from the origin to the corresponding point in space. So, how we looked at our last 2 vectors was treating them as position vectors. A vector, an arrow that sort of starts at 0, 0, or in 3 dimensions at 0, 0, 0, and points to the point in 3 space with the same dimensions as your vector. So let's take a look at that. Let's do another example in 3 dimensions, because that's the one I think that's harder to wrap your head around. So I'd like to try and do more examples in 3 space to give you a little bit of intuition how it works. Let's say we wanted to look at the vector v equals 1, 0, 1, and treat that vector as a position vector. If I wanted to draw out 1, 0, 1 as a position vector, what would be something that I would need to draw out? So I just do that and say, there it is, call it a day? Or is there something I should start with before trying to draw my arrow corresponding to that position vector?
Provide that.
Should provide the axes? I think that's a good first step. Yeah, draw out our x, y, and z axes. So here will be my z-axis. Here's going to be my y-axis. And I'll have another axis corresponding to depth. How far out in the x direction do I need to travel? In other words, how far out of the board at you do I need to go? If I'm trying to draw it out.
Just 1 space towards us.
Yeah, 1 space towards us, because we have an x coordinate of 1 unit. Stop. How about the y direction? Let's see. Let's get somebody in the second row here. I'll be a little bit quieter. How far out in the y direction do we need to travel, to the left or to the right? What's that?
0.
Yeah, there's no going to the left or going to the right on this one. So 0 units in the y direction. Finally, how about the back row? How far do we need to travel in the z direction?
This one.
This one? Up or down?
Oh, up.
Yeah, it's going to be up since our z coordinate is positive. So as a position vector, we need to go 1 unit along the x-axis, 1 unit upwards. And so our position vector v is going to look something like this. It's going to start at the origin, and it's going to end up at the point P which is equal to the point 1, 0, 1. It comes out at you 1 unit, goes up 1 unit, but doesn't go to the left or to the right from the origin at all. Why do you think a position vector is called a position vector specifically? What about the property of starting at the origin and pointing to, say, the point 1, 0, 1? What do you think makes that something that we would call a position vector as opposed to a, I don't know, some other type of vector? Don't want to use the word displacement yet because we haven't talked about what that means. What about this arrow pointing from the origin to 1, 0, 1? Do you think might give that intuitively an idea of what it means to be a position vector specifically? Yeah.
I'll take a guess and say it's starting at the origin is what makes it a position vector.
Cool. What does the origin have to do with position?
Well, if it's at 0, 0, then your numbers correspond. You can figure out the length pretty easily given just your numbers. I don't know exactly how to say it.
No, I think you're onto something. I think it's a good start.
Yeah.
So let's say you're at the origin. By the way, if I were to try to write out the origin in coordinates, what would it be here?
Oh, 0, 0, 0.
Yeah, it's going to be 3 zeros because we have a 0 in the x, a 0 in the y, and a 0 in the z direction. But yeah, the way when I think of position, in quick English lesson, position basically means where is something located. The way I like to think of a position vector is be egocentric for a second and think of yourself as being at the center of the universe. Suppose you are at 0, 0, 0 right now. And you want to get to the point at 1, 0, 1. How do you get to that point? Well, if you have a position vector pointing to 1, 0, 1, this point here, then basically the position vector is just a giant arrow that takes you from where you're currently located at the center of the universe, at the center of your own universe maybe, I don't know, and it takes you to the point you want to get to at 1, 0, 1. So position vector is just kind of how, if you're following like a map, so to speak, how to find your way from the origin to that point. Let's write that down. It's basically an arrow. You can, let's say v equals v1 up through vn. It's an arrow you can follow to find your way from the origin to the point at v1 up through vn. In other words, it's an arrow that tells you where the position of that point is. So, position vector has its name because it's basically telling you it's a way to sort of visualize the position of 1, 0, 1. You want to know where 1, 0, 1 is? Here it is. I have an arrow pointing to it. If I'm standing at the origin, that arrow is telling me exactly where to go to get there. It's telling me the position of that point. Any questions about position vectors? So, there's another type of vector that's called a displacement vector. When we're looking at a position vector, we're always assuming we're starting at the origin. And we want to say, how do we get from the origin to a particular point? But it could be the case that maybe we've traveled to the point 1, 0, 1, and now we're going to be looking for a way to get to some other point, but not from starting at the origin, starting from at a different point, 3 space or 2 space, or if we're some sort of upper level n-dimensional being in n space. And so a displacement vector, intuitively, is going to be a way to get from one point to another point. So here, we can say that we treat a vector W equals W1 up through Wn and Rn as a displacement vector from a point P1 to P2, which we'll often label as the vector P1, P2 with an arrow above it. If W basically starts at P1 and ends at P2. So in other words, a displacement vector doesn't tell you how to get to from the origin to some point. It's sort of a generalization of that, where we look at how do we get from one point P1 in space to another point P2 in space. So let's look at a two-dimensional example. Let's say now we're going to look at an example in the xy plane. It's trying to draw displacement vectors in 3 dimensions is even harder than trying to draw position vectors in 3 dimensions. Let's say we have 2 points. Our first point, P1, is going to be at -3, 1. Our second point, P2, is going to be at 1, -2 in our picture. So P1 will be at -3, 1 here. P2 is going to be at 1, -2, so here. The displacement vector that starts at P1 and ends up at P2 is going to look like this. And we can label this as the vector P1, P2 with an arrow above it. An arrow that starts at your first point at P1 here and ends at your second point at P2. So that the displacement vector from P1 to P2 is going to be P1, P2 a vector which we can talk about having two coordinates to it. What should I put in the blank here? If P1 is at -3, 1, and P2 is at 1, -2, what's going to need to be the coordinates of that vector, a vector that if we started at P1 and we traveled out by this amount, is going to end us up at the point P2. Meaning, let's say this is our x, this is our y here. Meaning, if we started at -3 and went out however many x units we have, we would end up at an x coordinate of +1. And if we started at an y coordinate of +1 and then traveled out this many units in the y direction, we would end up at a y coordinate of -2. So what should the x coordinate of our displacement vector be, do you think? In other words, how far to the right does this arrow point in order to get from the point at P1? Stop falling out. In order to get from the point at P1 to the point at P2. Yeah, no?
4.
Why 4?
Because it's just the difference in -3 to 1. You travel 4 spaces along the x-axis.
Yeah, because -3 plus 4 will get us to 1. I agree. This arrow, in other words, from P1 to P2 has to point 1, 2, 3, 4 units to the right from where it started. How about the y coordinate of our displacement vector?
-3.
Well, let's see. We're starting at a y coordinate of 1, and if we go -3 in the y direction, that'll take us to 0, -1, -2. I like it. Yeah, nice work. So if we start at -3, 1 and travel in the direction 4 units to the right and 3 units down, we're going to end up at our point P2 at 1, -2. This vector, by the way, if we had tried to draw 4, -3 as a position vector rather than a displacement vector, would have looked something like this. And this is going to be the vector 4, -3 as a position vector. If you're trying to look at 4, -3 as a position vector versus as a displacement vector from P1 to P2, how do those two vectors look? How do they compare visually? The position vector versus the displacement vector way of visualizing 4, -3.
They have the
No?
same magnitude, but they're like parallel. One is displaced by P1.
Yeah, they have the same magnitude, something we haven't defined, something we'll define in the next standard, which is basically how long is your vector. Not only that, they point in the exact same directions. They're both kind of pointing 4 units to the right and 3 units down. What word did you use starting with the word letter P for the day?
Wait, I said this displaced by P1. Is that what you mean?
I was going for the word parallel,
Oh,
which I think you
yeah.
used. Yeah, they're parallel to each other, basically meaning they're starting at different points, and even though they're traveling in the same direction, they have the exact same shape to them. The only real difference is where do they start? As a displacement vector, it starts at P1 up here at -3, 1. As a position vector, it will always start at the origin. In this case, since we're looking at 2 space, the origin is the point 0, 0. The origin in general is just going to be the point with all zeros, no matter which dimension you're talking about. The only difference between dimensions is how many zeros do you have. In R2, it's 0, 0. In R5, it's 0, 0, 0, 0, 0. In R500, it's I'm not going to say that one out loud.
If we wanted to get from P2 to P1, could we say that like negative P1, P2 is equal to P2, P1?
Ooh, that's an interesting observation. So now let's propose. Is that if let's say V is the displacement vector from P1 to P2 in general, let's say you have 2 points in some dimension and V is a displacement vector from P1 to P2. You're proposing that if we take negative V, that would be a displacement vector from P2 to P1. Why is that the case?
Well, if you did that, then the coordinates in our P1, P2 then will become -4, +3, which would take you back the way you came.
Let's see, -4, 1, 2, 3, 4, +3, 1, 2, 3. Yeah, that's a good observation. It certainly appears that way. That if you just took the negative of all the coordinates in your displacement vector from P1 to P2, that would give you a form of a displacement vector from P2 back to P1. Yeah, I would agree. And technically we have like we're one page out from talking about how do you multiply a vector by -1, but that's exactly how you would do it. The negative of a vector would just be take the negative of all the components. So I think you can say that. If V is a displacement vector from P1 to P2, negative V is the displacement vector from P2 back to P1. So in this case, P1, P2 will be the arrow from P1 pointing to P2. So if we were to take that same arrow and point it in reverse, that'll give us a displacement vector from P2 to P1. Oh, nice observation. Let's see if we can find a general formula for how to compute the displacement vector. And we'll do an example just in R2, but it'll generalize very easily to higher dimensions. Let's say we have a point P1, which is given by, and we'll call it x1, y1, and P2 is equal to the point x2, y2. Then what could we say has to be the coordinates of the displacement vector from P1 to P2? So in other words, if I'm starting at an x coordinate of, say, x1, where x1 could be any number, it could be 5, -2, 10 billion, square root of 3. x1 is a number, and we want to travel some amount of units to end up at an x-coordinate of x2, what could we add to x1 that'll take us from x1 to x2? So if we were to solve this equation, what would have to go in the blank, so to speak? This one's a little bit tricky because it's kind of a general problem, but I'll give you a hint. It's going to have to be some expression involving both x1 and x2. Derek, did you have a thought?
Yeah, x2 minus x1.
x2 minus x1, like that?
Yeah.
Well, let's see. We started with an x1, and if we subtracted an x1, that would get us to 0. Which if we then added another x2 to, that's a weird phrase, we would indeed end up at x2. Yeah, I think that's absolutely right there. We could say, in other words, that the x-coordinate of our displacement vector is going to be x2 minus x1. How about the y-coordinate of our displacement vector? In other words, if we're starting at a point with a y-coordinate of y1, and we wanted to end up at a point with a y-coordinate of y2, what could we add to y1 that would get us to y2? Someone other than Madeline and Garrett.
It would just be like the whole y2 minus y1 again.
I'm sorry, what's your name again?
Elizabeth.
Elizabeth. Yes, I think so. We could just, instead of saying x2 minus x1, we could say y2 minus y1. By the way, names. I'll try and have everyone's names down in a couple weeks and call on everybody by names. Madeline and Jared I've had in previous classes, so I'm good with them. But everybody else that I'm kind of in a class with for the first time, I promise I will try to work on names. It usually takes me about a couple weeks, to be honest. But yes, that's absolutely right, Elizabeth. We could just take the difference in the y-coordinates in the same way that we took the difference in the x-coordinates. The reason being, this expression, x2 minus x, if we added x2 minus x1 to x1, we would get to x2. And if we added this expression to y1, we would end up at y2. Just drawing a picture. This is our point x1 comma y1, and this is our point, let's say, at x2 comma y2. So here we have a y-coordinate of y1, here we have a y-coordinate of y2, x1, x2. If we look at the dimensions of this arrow, how far horizontally does this arrow need to point? Well, the x-coordinate of this arrow needs to just correspond to the distance from x1 to x2, which is just going to be x2 minus x1. And how far up does this arrow need to point? Well, it needs to take us up from a y-coordinate of y1 up to a y-coordinate of y2. And so the vertical change in this arrow is just going to correspond to this distance right here between the two y values, which is just going to be y2 minus y1 in the case. If you notice, over here, when we tried to use this, we could use this formula in the example we just did. If P1 is at negative 3, 1, and P2 is at 1, negative 2, then we could have also found P1, P2 by saying the x-coordinate is x-coordinate from the second point minus x-coordinate from the first point, 1 minus negative 3, comma, y-coordinate from second point minus y-coordinate from first point, negative 2 minus 1, which would have ended us up at 4, negative 3 in the exact same way. So that's how you typically compute a displacement vector. You just take change in x-coordinates, comma, change in y-coordinates. And if we were looking at a point and say R3 or R4, etc., you just have to do the same thing with each individual coordinate. Difference in first coordinates, difference in second coordinates, difference in third coordinates, etc. Any questions or comments about displacement vectors versus position vectors? Dr. Gerstle, if you just gave us a vector, say v equals, I don't know, 1 to pi. Pi. How do we know if that's a position vector or a displacement vector? You typically don't. I haven't given you enough information to say, is this just a position vector? Is this a displacement vector from one vector to another vector? You kind of have to know from the context how I'm referring to. Typically, if I don't say otherwise, it's going to be a position vector. So if I told you draw this out, I would typically be looking for the position vector starting at 0, 0, 0. But if I don't really specify, displacement vectors and position vectors are kind of the same thing in a sense, in that they're both arrows that have that much change in them in the x, y, z, however many directions. The key difference, though, is if you're trying to visualize them, at what point are your two vectors starting? Are they starting at the origin, or are they starting at a point P1 trying to point to another point P2? But as Madeline pointed out earlier, they're going to behave in the same way. They're going to look the same, it's only their starting point that's going to be different. They're going to be parallel, so to speak. Okay, so if we flip the page, we actually have a little bit of algebra that we can do with vectors, other than just computing displacement vectors, in the sense that we have ways of adding vectors together, and we have a way of multiplying a vector by a scalar. Let's talk briefly about each of those. So if we start with vector addition, we can say that if a vector v is equal to v1, v2, up through vn, and w is equal to w1, w2, up through wn, are vectors in Rn, we can make a new vector, which I'll call vector v plus vector w. What would your intuition tell you what we could do in order to add these two vectors together? No?
To add each dimension together.
Yeah, we're just going to add the first components together. We'll get v1 plus w1. We'll add the second components, v2 plus w2. And we'll continue on into adding the last dimensions together. Just going to give us a way to add each individual coordinate of our vectors together, like so. So, as a quick example, in R3, if I wanted to take the vector 1, negative 2, 5, and let's say I wanted to add to it 6, 10, negative pi. Because pi is a real number too. You should be able to have that as a component to a vector, even if it's not a nice behaving real number. It's going to be the first coordinate of the sum. Yeah, 1 plus 6 is 7. Second coordinate? 8. Negative 2 plus 10 is going to give us 8. I agree. How about the third coordinate?
5 minus pi.
5 minus pi. Can't really simplify that one because 5 and pi do not combine nicely. If you wanted to, you could write that as maybe negative pi plus 5, but it's just kind of saying the same thing. There's not a nice combination of 5 and negative pi into a single number. So adding vectors just means adding together their coordinates. There's another thing we can do with vectors called scalar multiplication. And the way scalar multiplication works is you have some vector. If v equals v1 up through vn is a vector in Rn, and R is a scalar value. We used this word before, scalar, towards the start of class. Anybody remember what I said scalar means? And don't say a mountain climber.
It's a single number.
Yeah, scalar is just going to be a single number. Then we can actually multiply the scalar by the vector. We can take the vector v, multiply it out front by our scalar, And what we would get is we're just going to multiply each individual coordinate by that scalar. R times V1, comma, R times V2, all the way up to R times Vn. So if, for instance, let's say we're in R4, and we had a vector, 4, 6, -3, -8. Let's say we had a scalar value. I'm going to pick the scalar value -1/2. And we wanted to multiply this vector in R4 by the scalar value of -1/2. What would the first coordinate of this product be? Where we've taken our vector 4, 6, -3, -8. So as a reminder, this is our vector, this is our scalar. What would be the first coordinate of our scalar multiple here? Where we've taken our vector, we've multiplied all the components by -1/2. What would we end up with in the first slide?
-2.
-2. We would get -1/2 times 4, which is going to be a -2. Second coordinate?
-3.
Get -1/2 times 6, which is a -3. Third coordinate?
Positive 1.5.
Positive 1.5, because -1/2 times -3 is going to be a positive 1.5. I like fractions personally, so I'm going to leave it in fractional form, 3/2. But if you wrote that as like 1.5 or something on a quiz or whatever, it's equally acceptable. I just like fractions. I'm a weird nerd like that. How about the last coordinate?
4.
-1/2 times 8 times -8, which comes out to a positive 4. Awesome possum. Yeah, that's exactly right. So Madeline, you mentioned earlier something about wanting to take a negative of a vector. Typically, how you would think of taking a negative of a vector is just taking a vector, multiplying by the scalar value -1, which according to that formula over there just would have the effect of multiplying all the components by -1, which just means taking their negatives. So that's how you would kind of represent that algebraically, is you're taking the scalar multiple of your vector, where your scalar happens to just be -1. Questions or comments about the scalar multiplication?
Actually, what about vector addition?
Okay.
So say we wanted to add a vector in R3 and a vector in R2, but then the z component is 0 in R3. Can you do that?
Ooh, so you wanted to take 1, 2, 3 plus -4, comma 5, something like that?
Sure, yeah.
Very cheeky of you. I actually had a question basically, I basically had this question on the next page. Yeah, if we had a vector in R3 and we wanted to add it to a vector in R2, can we do that? You don't think so?
No.
I would agree. I would just say you can't add those. In order to add two vectors, they have to be of the same dimension. Otherwise, it just doesn't compute. It would sort of be like if I were telling you, I want you to take the point 3, comma 5 in 2 space, and I want you to add 1 to that point. What does that really mean? 1 to both components, 1 to move it up by 1, over by 1. It's a little bit unclear, and so we would just say this is undefined. Yeah, good question. I'm making you all figure that. I was planning on making you all think about that. So when we come back next time, we're going to talk about geometric interpretations for each of these operations. Meaning, geometrically, what does it mean to add two vectors, or visually, I should say. And visually, what does it mean to take a vector and multiply by a scalar? And we'll talk about why we might care, what reason we might have to care about doing those sorts of operations. Well, in that case, I hope you have a good first weekend back. There are practice problems posted from from sections 1.1, 1.2 you can look at. There's going to be some practice problems on stuff we didn't get to, so if it looks like we haven't defined something like, say, standard basis vectors, don't worry about doing those problems yet, but you might start taking a look at some of the other ones, get some extra practice in. And I will see you all on Monday, where hopefully we will get through the rest of standard stuff. Good day, everybody.